Is there any questions about anything from last class? Okay, seeing none. The Concordia research was going to come, the research office was going to come and give a presentation. They couldn't come in the last minute. So I'll just show you the slides that they sent me. I don't know any of the details about this, but it's just something for your information for students. So there's an innovation fund within the faculty. I guess it helps fund like startups. So if you have an idea, for a business idea for a startup, or you're already running something, then they have money that's available. They have kind of like two phases. So in the phase one, it's like kind of pre-deployment, and it's up to $10,000. And then they have up to $50,000 for kind of building out an MEV prototype. There's a couple examples. I'm sure the people that would have come would have told you the full story behind these. I don't know what the full story is, but they're, I guess, companies that were started within the faculty that use this fund in the first days to get started. So if you're interested in learning more about it, I'll just leave this up on the screen for a minute. And of course, it will be in the recording as well, so you can go back and find the contact information. But they will have 2 question and answers with pizza. And also you can email any of the 3 people there to ask them questions about it. Pascal was the one who was going to come to class, but couldn't. Okay. Okay, so in today's class, we'll continue looking at high-level security evaluation methodologies. Last class, we looked at STRIDE. This class, we're going to look at something called evaluation frameworks. So evaluation frameworks, again, are high-level. High-level just means that it's not limited to software or hardware. You can use it for pretty much anything. But of course, with that breadth that you get, you probably don't get a lot of depth at the same time. STRIDE, and later we'll talk about attack trees. STRIDE is really about evaluating the security of one thing in particular. Evaluation frameworks are about comparing the security between different alternatives. So that's mainly how they differ. Attack trees are even more narrow. It's not just you're evaluating one thing, you're evaluating one potential attack or one security property that it should hold on one thing. So if you have one thing, you might have 10 attack trees for it. You would have one STRIDE analysis. And then if you had 10 things, then you could do an evaluation framework. The main idea of an evaluation framework is to sort of illustrate what economists like to say, which is that there's no solutions, only trade-offs. So generally, if there's competing ways of doing something, it's probably because there's not one way that's like strictly better than every other way. It's probably the case that they have pros and cons, and depending on what you want, you might prefer one over the other. And the deliverable of an evaluation framework is a chart, a comparison chart, and it's basically, you'll see it a lot. But it basically like compares all the different alternatives, and then you have a set of properties or criteria that you compare it to. Okay, the deliverable is not anything that you have never seen before. If you see comparison charts all of the time, right? If you buy a car, it's kind of like, okay, here's 3 different cars, and then here's a bunch of comparisons between them along a whole bunch of different specifications. Or, there's different kinds of bank accounts or different banks, and here's the properties that they have, okay? So an evaluation framework is just that, but it's for security. We try to use it to give a neutral presentation of information, which means we're not trying to convince you. So a lot of these are trying to convince you that their thing is better than the other. The way they convince you is they have all the dots and nobody else has all the dots, for example, okay? What we try and do with evaluation frameworks is it's more neutral. We don't try to sell. It's not like a sales pitch kind of thing. It's just sort of like, here's 10 different ways of doing something. Here's a bunch of things that you might want from a system that does this. And here's like which ones achieve which properties. The other thing we try and do with an evaluation framework is we care more about security than just security itself. So you're going to have a bunch of properties that are relevant to security, but there's other things that people factor in when they make decisions that are not necessarily strictly about security. A great example would be cost, right? I can give you a super secure solution, but it costs $1 million. And then I have one that's pretty good, maybe not as secure, but it only costs $10 per user. Which are you going to go with, right? So cost is a factor. But there's other things too, like deployability, like how easy is it to roll the system out? Do I have to install something on everyone's computer, right? I'm Concordia, I'm implementing some software security solution. It gives me security, so that's the pro, but every single computer on Concordia has to update, every phone has to update, right? So that's like a hidden cost. You can think about the usability. Now that this thing is installed, everyone has to have this extra app and they have to put an extra pin in and they have to link their apps together and they have to do that every time they log into the system or something like that, okay? So that's going to be a usability burden. So what we try to do in evaluation framework is we try to take a holistic, basically anything you can think of that would impact someone's decision, you're going to try and include it. So the rows of the table will be the different alternatives that you're comparing. The rows should actually be alternatives, not sort of complementary mechanisms. Like you might have rows like, I don't know, I'm going to use intrusion detection, or I'm going to use personal firewalls, or I'm going to use antivirus. Well, the fact is you could use all three of them, right? So they're not really alternative ways of doing something. So we like to do evaluation frameworks where they're truly alternatives. And you usually are just choosing. If you're doing X, you're not doing Y. If you're doing Y, then you're probably not doing X. Generally, we also exclude from evaluation frameworks things that are just like strict improvements over something else, okay? So like we generally don't evaluate like version 1 of something and version 2, unless if version 2 like creates new problems as well as new solutions. If version 2 is strictly better, then there's no point of doing an evaluation framework. So for example, for Wi-Fi, you wouldn't compare the WEP protocol to the WPA protocol to the WPA2 protocol because everyone would use WPA2 instead of WEP. There's basically no reason to use the old generation. We try and do apples to apples comparison. So we're trying to compare things that are solving the same problem, not things that are slightly different. So like a firewall and intrusion detection are different. They have to do with network security, but they're not really solving the same problem. So we try to compare things that are basically solving the same problem. And we like to compare approaches as opposed to the brand names of doing certain things, right? So for example, if I was comparing, let's say I want to buy a little car, instead of comparing the Tesla Model C to the Prius to the Golf specifically, I might compare them as a category. I might say, okay, you have one's electric, one's hybrid, one's gas. The electric, it doesn't matter that it's a Tesla as opposed to a Hyundai or whatever. We're comparing that as a category of solutions. But sometimes you'll give brands as examples. So you'd be like, here's the category, and then, for example, like a Tesla or something like that. Yeah. Yeah. Silly questions are welcomed at all times.
Every solution or systems falls into the OSI model, right? So we know OSI model has 7 layers. So where the evaluation starts? Why should we start the evaluation? Like this section needs to be secured more.
Okay, so this isn't about necessarily finding like where to secure things. It's more like if you have a bunch of transport layer protocols and you want to compare them, right? Then they're all the same. They're all doing the same thing. They're all in the same layer. And this is just strictly about comparing which one's better than which. Yeah. So it's not going to help you find problems. It's not like Stride. It's strictly just a comparison between existing options. Other questions? Okay. So those are the rows. So the rows are the systems or approaches. And then the columns are like, what does it mean to be secure, or what does it mean to be useful to someone in terms of other properties beyond security. This sounds really easy, making these charts. It is, like conceptually, it's super easy. The hard part is when you sit down and you have to try and figure out what's good criteria and what are all the different approaches and things like that. It actually is a lot harder than it seems, but we'll try and make it look easy, at least for the lecture. So if you have to come up with columns for things, so usually in assignment 1, so I'm not sure about the assignments yet. I have to check one thing with the office, but usually assignment 1 would be to create an evaluation framework. That's usually what we do. So it's something that you may have to do. So sometimes it takes a lot of iteration. So you sort of pencil in columns. Maybe you evaluate the system. You realize, oh, these 2 columns are really measuring the same thing. And so we don't really need both of them. Or this column really should get split into 2 different columns because it's kind of measuring 2 things at once, that type of thing. What we do is we always phrase the column positively, which means that you want it. So for example, let's say there's an attack. I could have a column, here's 5 systems, and I could have a column that's like, it's vulnerable to this attack. Yes, no, kind of thing, okay? The problem when I read that chart is I don't know, like, is it good to get a yes or is it good to get a no? I would have to read the column title. So the column title is like, it's vulnerable to this attack. So in that case, a no, you don't want to be vulnerable to the attack. So a no is a good thing, okay, as opposed to a yes. So what we do is we try to change the wording of all the columns so that yes is always good. Okay, so instead of saying it's vulnerable to the attack, we'll say it's resilient to the attack. And then if I just sort of glance at the table, if I see a lot of yeses, I'm like, okay, that's doing well. If I see a lot of nos, I'm like, that's not doing so well. And instead of yeses and nos, we usually use dots. Like a dot, you get it or you don't. Okay, so then in each cell, we kind of use like a full dot, which means it fully satisfies it. We can leave it empty or have an empty dot, which means it doesn't satisfy it. And then I like to sometimes give myself the ability to have a half dot because sometimes, there's things that kind of fall between where it's better than doing nothing, but it's still not as good as the best thing. This is not strict. You can use any metric itself. You don't have to use dots. Anything, an evaluation framework encompasses any kind of thing, but most problems can get simplified to this metric, okay? You can usually simplify every problem down to something that's simple as, full, partial, or none. You also don't necessarily need a partial for every single column, so it depends on the column itself. Some of them are very clear cut. Some of them are a little more, there's different ways of doing things. Okay, if you write an evaluation framework and give it to someone, you're going to give them the chart, so they're going to look at the chart. But they also need to know, what does every column mean? And for every column, what does it mean to get a full dot? Like exactly, what does it mean? What exactly is a partial dot mean for this particular column? So you basically have to walk through every column. You have to say what a full, partial, no dot means for every single column. And then when you actually do your evaluation, you also need to say why you gave a system a full dot as opposed to a half dot. Okay, so evaluation frameworks have a lot of explanation. Basically, every column is explained, and then every cell in the table is also explained somewhere. And so someone can look it up and understand why it looks the way it does. The other thing I'll mention is that different people doing the same evaluation framework will not necessarily come up with the exact same table. Okay, so your columns could be different depending on what you think of. Even if you come up with the same columns, you might differ a bit between what's a half dot, what's a full dot, or you might differ in deciding whether a system, achieves that dot or not. Okay, so there is some room. It's not like an exact science where, a room full of 30 people are all going to do it exactly the same and produce the exact same table. Okay, and that's fine. That's acceptable. But what should be the case is that whatever systems are kind of dominant or doing better, they should generally be doing better across everyone's tables, even though their tables are slightly different. Okay, any questions so far about this? Okay. All right, so we'll come back to this in a second. And when we come back to it, I'm going to do an example that's related to passwords, just so that we can see what it looks like. Before I give the example, though, I want to tell you a bit about passwords, just so that everyone's sort of on the same page in terms of how passwords work. Okay, so a password is something that you use to lock your account to you. So generally, if you go to a website, you're going to sign up for a service. You're going to have some sort of unique identifier for you, a username or an email address, and then you'll have your password, okay? And the way it works is when you register a password, you send your password to the website. You send it over a channel that's secure, okay? And the website, though, once it reaches the website, it drops out of the secure channel. So the secure channel is just between you and the website. And so the website does see your password in plain text. They know exactly what your password is, okay? Then what they'll do is they'll take your password, and in attempt one, not the most secure way, but one way of doing it, is they'll just drop it in a file, okay? So they have some file that's sitting on the server. It has every username, and it has every password. Then later, what will happen is you'll come back to the website, you'll put your password in, and then it will go into the database. It will say, okay, Alice is trying to log in. This is the password Alice is sending me. This is the password I have stored. Are they the same? Yes, then it's the same user. Are they not the same? No, then you get an invalid password. Okay, so we'll get there eventually, yeah. Okay, so this is the basic kind of approach. Okay, so what are all the security vulnerabilities? So, yeah.
The server gets hacked, the whole database will leak.
Okay.
And the password will be known.
Okay, so if someone breaks into the server, password file is leaked, right? So all the accounts are compromised. The attacker can log into any account. Plus, if you use that same password on other websites, which lots of people do, right? Then someone might take the password that got leaked from site A and try it with the same usernames or emails on site B, C, and D, and they may be able to get access as well, okay? Do password leaks ever happen? All the time, right? You hear about it in the news. Now your operating system warns you. Apple, like every time I set a password, it warns me and says, you know, you've used that password on 10 sites. You shouldn't do that. Or we've seen that password in one of the leaks, you know, that kind of thing. Okay, so that's one vulnerability. What's another vulnerability in this scheme, if you can see any?
Maybe the connection between Alice and the server might be cut by someone.
Okay.
And they will be able to know the password.
Okay, so let's say someone's in the middle here, right? And the password, remember, the server needs to get it in clear text, right? So if someone's in the middle, they might be able to just reach in and grab the password off the wire and then read it. Now they know the password. Any other ideas?
Third-party sites.
Okay, so a third-party site. Now in this case, we'll spend a lot of time on like third-party sites a little later because we're going to look at weaving content from multiple sites. In this case, you are sending your password directly to the site itself. So even if the web page is weaving stuff together, they won't get a copy of your password. But if they're running, say, some JavaScript or something on the site, there are ways that they could potentially get it. Yeah. So cross-site scripting type of vulnerabilities. Other ideas? Okay, so let's we'll kind of walk through it from the user all the way to the server and look at what the vulnerabilities are. So even before the user types the password in, right, or as they're typing the password in, there is a chance that someone surveils that. Okay, so someone might see it get passed in. So that's called shoulder surfing. There's this video, there's a whistleblower, I'm sure you've heard the name Edward Snowden, and sorry? Yeah, it's from the movie, yeah. So there's two movies. So there's a documentary, and then there's a like a live action movie starring an actor, a Canadian, I forget his name, who plays him. One thing he does at one point is he's in a hotel room and he wants to put his password in. So he has this big, elaborate like contraption that's kind of like a quilt. And he puts his head in one end and he has his computer in the other end. And then he types his password in. So I have a clip from the movie. You can kind of see him do it. Yeah, and this clip kind of weaves the documentary from the other one. So he is concerned about the journalists that are there with him. Joseph Gordon-Levitt is the actor, by the way. But he's also concerned about surveillance, right? There could be video cameras anywhere, and it's top secret, like highly classified documents and things like that. So it's not something that you would maybe do, you know, when you're putting your password in for Instagram or something. But for extreme circumstances, you might do that kind of thing. Okay, so that's shoulder surfing. So that's on the wire between, not on the wire per se, but like between the user and the actual computer itself. Now, when your password goes into your computer, right, you typically are going to put it in through the keyboard. Okay, the keyboard then passes it to the operating system, to the kernel, and then it goes to the application that needs it. Then it's going to drop out on the network, and then it's going to send across the network, okay? So there's a lot of places in your computer as well where there might be potential, if you have malware, it might potentially lift your password off, okay? So one example would be keystroke logging. So this was an example actually from Concordia itself. So in Concordia in the library, one day they walked around, or someone reported, I'm not sure how they found it, but they saw that there was all these like dongles that sit between the keyboard, which is, these aren't laptops, so there's a physical keyboard, there's a wire that connects to the computer, and then in between it there's a little dongle, and that dongle was a keystroke logger. So every key that was pressed on the keyboard was being recorded by that device. Then the device may, if it has Wi-Fi, it might like just email it or drop it in a location, or maybe the attacker comes back a week later and then they just put it in their pocket and leave with it. So there's different ways they work. But every single password, you know, is getting logged. Now it is a raw text file, right? Because it's before the computer. So like even if someone went up and pounded on all the keyboard, like all that stuff would get recorded. It doesn't know what is a password, it just knows about text. But if you see someone type blah, blah, blah at concordia.ca, enter, then the next thing is probably a password, you know, enter, and you can easily write a script to test that out, kind of thing. Okay, then you can have malware anywhere in the stack, so it could be on your computer, hopefully not at the kernel level, but it could be in the application that's using it. It could be on the network interface, anything like that. Then we drop the password on the secure channel. And in this case, we are saved by the fact that we do have pretty good secure channels. Okay, so generally we're going to use a protocol called HTTPS. This is something that is not bulletproof, and we'll spend 3 lectures a little bit later talking about this protocol and all the different ways that you can defeat it. But for now, we'll just assume that it's pretty good if you use HTTPS. HTTPS gives you end-to-end security, so that means that the lock starts at the computer, it ends at the server, and if there's people in between, which there's always, you know, routing machines and things like that, middleware boxes, they're always in the middle. They just see encrypted data. So they do see it, but it's in encrypted form, and it doesn't get decrypted until it makes it all the way to the server. At least that's what HTTPS promises. Okay, so they call it end-to-end encryption. And then the last thing is you could dump the database if you can breach the server. Now, there's a few things we can do about the last one. So one thing we can do is, instead of storing everyone's passwords in plain text, what we could do is we could use a tool from cryptography called a hash function. A hash function is kind of like a one-way mapping. So it turns an input into a random-looking output. You can't go backwards. So once you have the output, you can't go back to what the input was. But if you have the same input, it will always give you the same output, okay? So the way it works here, just to confirm that it works, is the server, the first time Alice logs in and sets like registers for the website, they do see it in plain text, okay? So the server sees it in plain text, but then the server very quickly hashes it. They store the hash output, and then they delete the input. So they never look at the input again, okay? Yeah?
Is it better if Alice is the one doing the hash?
Okay. So let's save that question. Let me explain this, and then that's a great follow-up question, okay? Then Alice comes back and she logs in a second time. Again, she sends it in plain text. The server sees what she's alleging is her password in plain text. The server computes the hash of what she sent, and because if you have a hash and the same inputs map to the same output, right? Then it will produce the same result, okay? So even though it just has a hash of it in the password, it will hash whatever she gave it, and if it matches, then they'll assume it's the same password. If it doesn't match, it has no idea what her actual password is. It just knows that this isn't, whatever she's telling them is not the actual password, okay? All right, now here's an idea. So what if Alice hashes it instead? Then the server never sees it in plain text. So Alice sends the hash of her password. The server records the hash of her password. Then later she comes back with the hash of the password. The server stores the hash of the password. In this case, it's actually exactly the same as this scenario, where the hash of the password is the password, effectively. And the hash of the password would be sitting here in this database file. So even if someone grabbed the file, they would get what's effectively the hash, or the password itself. So it's a great idea, but it doesn't work. It doesn't actually do anything. Now, the advantage of this is what happens if the database gets dumped?
They could analyze the frequency of the passwords to try and guess if there's a common password in there.
Okay. So before we get there, first, can they just read out everyone's password?
No.
Okay. So that's the most obvious thing. Okay, so they can't just read everyone's password out. Okay.
If more users use the same password, they're going to have the same hash.
Okay, so there's frequency type of analysis. If 2 users have the same password, it will show up as the same hash. Yeah.
If you do this, you can also sort the hash, so that each hash is unique to its own user.
Yeah, okay, we'll get to that too. Yeah, so that's a good idea. That's a countermeasure.
Or we can use the rainbow table.
Okay, so that's another problem too. Yeah, so salts and rainbow tables, they're coming in a second. Well, actually, explain a rainbow table. That's actually what I want to say next, if you know what it is. Can you explain it, or?
So basically,
Okay.
in the table, we've got a base password, and then we get the hash of it, and then we get the hash for that hash. And whenever someone is able to crack a certain cell in that table, then they know they could go backwards and crack the initial password.
Okay, so that's a little more sophisticated. It's a little simpler than that. So,
Pre-computed hashes, like
of what though?
Passwords,
Okay. So yeah.
passwords of around the world, something like that.
Okay, sure. Okay, so remember, if you hash the same thing twice, you get the same hash output. So if you have a guess, I can't reverse the hash. So I'm looking at this hash, I can't go backwards. But if I have a guess at what it is, can I check whether my guess is correct or not? Yes, okay. If I'm wrong, it doesn't help other than it wasn't that password. But if it's right, then I've cracked the password, okay? So what I can do is I can just guess every word in a dictionary. Or I can get lots of common passwords where passwords got leaked without being hashed. I could say, oh, those are the types of passwords that people use, and I can guess all of those. Or what I could do is I could say, a lot of times people will like replace an I with like because it like requires one number and one special character or whatever. So I'll take my dictionary of English words and then I'll just replace, symbols or things. It's called leet speech. And so I'll make a whole bunch of variants, okay? How fast can I do this? Hashes are like nearly instant, okay? Computers can do hashes, like I forget what the hash rates are. Bitcoin does tons of hashes every second. But you can hash really, really fast, and you can guess and create guesses really, really fast, okay? And the next thing is, let's say I do it. So that's what a rainbow table is. A rainbow table is just a bunch of guesses and what their hashes are. And the nice thing about it is if I do it for my dictionary, you don't have to do it. I can just give you my rainbow table. And then you don't even have to do the work of hashing all your guesses. You just look up the thing that you're trying to crack into my rainbow table, okay? So different people can keep adding to a rainbow table as long as the hash function's the same. And most people use the same hash function. They'll use, or a couple from a small set of hash functions, MD5, SHA-3, or SHA-256. Okay, so rainbow tables, so hashing the password is strictly better than not hashing it. But at the same time, it's not that secure. If people are choosing simple passwords, then you're going to be able to guess it. And rainbow tables is the ability of one person to do all the work of all the hashing. They have a computer with a bunch of GPUs. Then they just put it as a BitTorrent file, and then everyone can download it, and they can do it nearly instantly.
And there's also the issue of if there's a weak hash being used, then they could probably do some collision and then
Okay, yeah, so weak hashes also are relevant. Because I do crypto, I'll tell you that you're right that when a hash function breaks, hashes usually have two properties. So one property is that you can't go backwards, and then collisions is the other one. The property that breaks first is collisions, and collisions doesn't help you here actually. So you would have to break the other property, which is that to go back. And even old hash functions like MD4 and MD5, people haven't broken that pre-image resistant yet. They've only broken collision resistance. So yeah, even an insecure hash function is still safe for this kind of application. But yeah, but it's a good point. Okay, then what we can do as well, this is just another like tweak that we can do, is so it was mentioned that we could add salt. What's salt? Salt is just a random number, okay? We add it to every password, and we write the salt down. I wish I had a slide that showed it, but we write the salt down into the file itself. So if you go and look at Alice, you'll see the hash of it, and you'll see her salt sitting there as well. It's stored, okay? So the attacker can still do a rainbow table, but the difference is I can't use a rainbow table that someone else made. I have to do it from scratch myself, okay? So salt don't solve rainbow tables per se, but what they do is they force you to do all the work yourself.
Is the hashes unique even though the passwords are?
So because the salt is stored here, and when they breach the database, they get the salt, it's not unique anymore because you have the salt, yeah? But what it does is it just means that I can't use someone else's rainbow table because they didn't have that salt value. And then what the website should do is they should use a different salt for every user. So I also can't crack all users at the same time, right? I have to really target, I have to say I'm attacking Alice now, and then I have to do the full rainbow table for that value of the salt. And then if I want to crack David later, I have to use his salt value. I have to start all over again, okay? And then another thing you can do is instead of storing the hash output, you could make them hash it 1,000 times and then store it. And so this takes a little more time to compute, so it slows it down. Now, the problem here is it also slows it down for the website just when they're checking passwords. So someone puts their password in, now it has to hash it 1,000 times and then check it, okay? But if you're doing a rainbow attack, right, you're guessing faster than most websites are handling passwords. And so it's probably going to hurt the adversary more than it's going to hurt you as a website. So it's hurting both of you. It's slowing that process down, but you're really, really slowing it down for the adversary that has to do a rainbow table by doing iterated hashing. So there are standards like PBKDF2 that have all this kind of stuff worked into it, and that's how now people will store passwords. Okay. All right, any questions about that? Yeah.
We don't use Argon 2 anymore, or it just
Use which?
Argon 2?
I don't know. I don't know that algorithm. Yeah. Okay. All right, now let's talk about passwords themselves. So we'll take a step back. So the vision for passwords, first off, way back in the day, computers didn't have passwords. And actually, computers were just used by one person. So that's like the original. And then people started sharing computers, but there was no users or accounts. And you know, if I sat down at a computer, I could access all of your files and vice versa. So people said, we need accounts, we need passwords. And the vision was that you would have a different password for every computer that you used, and that you would remember it in your head. You'd never write it down or anything like that, okay? So that was the original model. Then when we moved to the web, it just sort of got moved from computers to websites. So now there's lots of different websites. You have a password for each website. They're different, and you memorize it and keep it in your head. But then the web exploded, and now we have accounts at 1,000 different websites, and it's impossible now. Okay, there's no way that you can memorize 1,000 unique passwords and actually remember which one's which, unless if you have some sort of system, you know, for doing it. Okay, so passwords sort of became untenable, and so what people said is, well, can we do better? Is there anything we could use instead of passwords? So you want to log into a computer or a website, instead of using a password, what could you use?
Something that you are or something that you have.
Okay, so the broad categories of authentication are broken into something you know, which would be like a password, something you have, and then something that you are. Yeah. So what are some examples of haves or ares?
Key or biometric.
Okay. So biometric would be one. Okay, so biometrics would be, face, iris, fingerprint. My computer has a fingerprint reader on it. I can log in or give system permission routes. Yep, secure. Okay, so then hardware would be like something you have. So like some sort of like token that you walk around with, like secure key or an RSA token or something like that. Okay, one-time codes. So some sort of thing where you put the phone in the loop. So you have a username, you have a password. Two-factor authentication also would fall under that. We send a code to your phone or to an authenticator app or something like that, and then you put in the code as well. So fingerprints, two-factor, secure tokens.
The SSOs, like single.
Okay, single sign-on. So instead of me creating a username password for this website, I'll just use my existing Facebook, Google, Apple, whatever account. Other ideas? What about passwords themselves? So passwords, you're probably thinking like alphanumerical. Is that the only kind of password? Anyone use Android? What do you do to unlock it? Yeah, so you have a pattern or you draw. There's some research that shows that patterns are easier to remember than other things. And there's a bunch of experiments with like, could you show someone a picture and ask them to click? And that's where they click is kind of like their password. And then they come back later and they click on the same things. So those are called graphical passwords. Any other things? Sorry? Okay, so fingerprint, yeah, biometrics. Face ID as well. So my computer has a fingerprint and my phone has Face ID. Okay, so I think we did pretty good. There's a few I can think of, but let's go through them. Okay, so two-factor authentication. So this could be based on text message, but there's other ways of doing it as well. Graphical passwords, so like a swipe pattern. Biometrics, so Face ID, fingerprints, that type of thing. Another one's crypto keys. So you could just have like something that's stored on your computer, like a secret key. And the advantage here is there's no user interface where you have to type anything in. Your computer just goes, they grab it, and then boom, you're in. So if you use SSH, for example, it just logs you in once you set your keys up. If you use like Bitcoin blockchain kind of stuff, you usually have a password that locks the key. So you can have a key that's locked with a password, but once you unlock the key, then it does things with your key. Okay, another one is password manager. So in this case, we do passwords, but instead of me remembering them in my head, my computer remembers them for me. It generates them for me, so they're really random and secure, and they have special characters and all of that type of stuff. And maybe I have a master password or something that like gets me into the password manager, but other than that, I don't have to type passwords in all the time. So personally, this is what I use. This is the solution that I like. Sometimes I'm forced to use one of the others. Hardware tokens, so this is like an RSA token. There's other ways of doing it. This one is kind of like a two-factor authentication where there's a code. You type the code into your computer along with your username and password, and it lets you in. Single sign-on. And there's other things too that are related to passwords that we won't consider. So like personal verification questions. So usually that's for like resetting a password as opposed to authenticating. Although of course, if you can reset a password, you can also authenticate with it. So it's sort of relevant, but we won't consider it. And then there's things like CAPTCHAs, or if you put your password in 3 times, it locks you out. Yes, to prevent like exhaustive search attacks, brute force attacks. Geolocation, so like if I am logged into Gmail, I say keep me logged in, but then I fly to Europe or Asia or Africa or somewhere, and then it's like, oh, you are somewhere completely different. I'm going to make you log in again, even though you have the secure session already. Okay, so what we're going to do is we'll take these 8 and we'll put them into an evaluation framework. Okay, so an evaluation framework, we have our rows, and now what we want to do is we want to come up with columns for them. Okay, so to come up with columns, what we'll do is we're going to look at properties that have to do with security. And then, like I said, we want to consider other kinds of things like cost and how many servers do we have to change and things like that. And so Other categories will kind of lump into deployability, meaning how hard is it to roll the system out? And then usability is like the human factor. So with passwords, the human factor is like one of the key aspects, okay? And so we'll try to come up with columns in usability, in deployability, and in security. Sometimes we call this a UDS framework for usability, deployability, and security. It comes from this paper, and this paper has an evaluation framework for password alternatives. I'll show you their evaluation framework at the end. It's going to be a lot more detailed than what we're doing in the lecture, but we'll try and do it ourselves first, and then I'll show you what it looks like, if you go to a real academic paper, because it's obviously going to be a little more sophisticated and detailed. Okay, so the first thing we'll start with is usability. So usability is, we're going to do 2 lectures on usability next, I think. And so I'll give you some methodologies where you can evaluate usability very thoroughly. But for now, it just has to do with how easy is it for the system, for the user to use. And the idea is that if you have a system that's not easy to use, users, A, won't use it. They'll make mistakes, which will slow them down or cost money. They may try and find ways to circumvent it. So they might try alternative ways. So instead of doing the secure way, they'll do an insecure way just because they don't have to do that authentication step. So these are all drawbacks to usability. So if you have a system that's very secure, but it's weak on usability, it might not actually be beneficial. It might not actually increase your security to deploy it, because if everyone hates it and they try to avoid using it, you might end up less secure than you were before, okay? And then deployability will be like cost and things like that. Okay, so from a usability perspective, let's go back to this list here. Are they kind of all the same in terms of usability, or can you see some differences where some of them feel like they maybe are easier to use and some of them are maybe harder to use? And what are those differences? Okay, so biometrics are easier than a password. Why? It's an obvious thing, but just say why.
Because you always have it.
Okay.
You don't need to remember it.
Yeah.
Also, in any scenarios, you can use it. For example, your fingerprints or your face.
Okay. So it was nice. You broke it down to 2 things. So with a password, you have to remember it. So biometrics solves the memory part. So now I don't have to remember it anymore. And then there's the actual using it. So when I put a password in, I have to type it out. It takes a few seconds. If I have some sort of disability, maybe I broke my hand, I have a cast or something, it could take a lot longer. But with a fingerprint, it's easier. Now, of course, if I did something to my finger, right, then you have the flip problem, right, where it's harder to do. But anyways, it's effortless to authenticate with a fingerprint. It's not 100% effortless, because I still have to put my finger down. Is there anything on this list that's actually 100% effortless? Oh. Okay, so password manager, yes, especially if you don't have the master password or you just put it in once, it just automatically does it. Single sign-on, if you're already signed in, then it's all good. And then cryptographic keys would be another one. So keys are just, even if you're not signed in, even if you don't have a master password, it grabs the key and it's done. Like, you don't have to do anything. So cryptographic keys, I mean a file that's on your computer. If by security keys you mean like the USB things that. Oh, sorry, I know what you're saying. Yeah. So secure keys are that. Yeah. So they're cryptographic keys, usually wrapped with a biometric though. So it's. Correct. Yeah. Yeah. So it's actually a combination. So it's a cryptographic key with a biometric to access the key. So the key is stored in a way that the operating system can't see it until you authenticate. Yeah. Okay, so that's one. So how many times do I have to remember it? What do I have to do to actually authenticate? So there's going to be some differences here. Any other differences that you can spot in terms of usability?
Some of them you still have to have an object with you in order to use them, like the hardware token or the 2-factor authentication.
Okay, so I have to carry around this token. If I lose the token, then I can't authenticate. If I lose my phone or my kid's playing with my phone, then I have to go and grab it out of their hands and they're screaming at me because they want to play Roblox. never happened. Yeah, so that's the kind of thing. So that's a usability concern. Anything else?
Also, two-factor authentication, maybe the sending server is down, so you may not receive the pass key for an hour or something.
Okay, so there could be some sort of, so that might go more to deployability, but it could also go to usability. So if there's some sort of disruption, it's easier so you could think of the disruption of all of them. So passwords, it's in my head, so there's not a lot to disrupt it. Two-factor, I'm dependent on a server. Graphical, it's kind of like passwords. Biometrics, it's kind of with me. Keys, if I'm not on the device that I stored my key, I sit down to a new device. Can I log in? No. So that's another usability property that's sort of related. Password manager, again, it's tied to my specific computer. Hardware token is something that I could lose. And single sign-on is yeah, so it also has a server in the loop. So I have to ping off Facebook server. If it's down, then I'm not gonna get the answer. What about two-factor authentication versus a password? Which would you rather put in? If you had a choice, you didn't care about security, would you rather just put your password in and be into your account, or would you rather would you want to copy a code out of your text messages and put it into the website? Okay, only password, right? So it's you going to copy something out of a text. It's some like long random thing. It's kind of like hard to remember what it is. You're kind of like looking back and forth. Do you make mistakes?
Or there's usually like the magic links where you just have to click on it and you're signed into your account.
Yeah, exactly. Yeah. So there are ways of polishing all of these as well. So when we rank them, we can take that into account as well. So like two-factor, like one thing that I love is that my phone is an iPhone and my computer is a MacBook. I have iCloud, so I can copy and paste from my phone. I can copy on my phone and paste on my computer. So I can just copy it on my phone and then paste it so it has a shared clipboard. But like those are the kinds of things that you don't always have. Okay, other usability things that you can spot? So I think we did probably pretty good. Let's see what we came up with. Oh, sorry, I guess I have some points, high-level points about each of them, and then we'll go through them. Okay, deployability. So this is basically how easy is the system to set up? What are the barriers or frictions to setting it up? And then security is how secure the system is. So we'll do the same exercise for deployability and security in a second. But for now, let's look at usability. Okay, so nothing to memorize. So do I have to memorize something or not? Easy to learn was something else that was suggested in the paper, like how cognitively demanding is it to try and figure out what's going on? Can you use it so when you're typing the thing in or you're swiping your fingerprint or whatever it is, how easy is it at that point? Nothing new to carry, meaning like do you have to carry a token around? And it could be something old to carry, like you're probably carrying your phone anyway, so two-factor is a little better than RSA, but it's still worse than not having to carry anything at all. Right? So that's where if I have nothing new to carry, I give it a full dot. If I have to carry around this RSA token, it's not getting the dot. But if I have to carry my phone around, I might give it a half dot because it is something I have to carry around, but I'm also probably carrying it around anyways. Scales to thousands of passwords. So the ones that don't would be like you memorize your passwords or you memorize your graphical passwords or whatever. You're not going to memorize 1,000 different things. Errors we talk about, and then recovery from loss is the idea that like, can I lose things or can servers go down and things like that, and I can't authenticate as a result. So how resilient is the system to those kinds of things? Okay, next is deployability. So let's just go back to the list. So you're Concordia, and you decide that, hey, instead of everyone using passwords, we're now going to use single sign-on, we're now going to use fingerprints, we're now going to use whatever. Okay, so from an IT perspective, are there ones that you like or you don't like? And then also from the user's perspective, right? I'm a user and I'm being forced to now use one of these things. Are there deployability concerns for me? So either of them are acceptable, but what are your ideas? Are they all kind of the same if you want to roll these out, or do some of them have a bigger impact than others?
Single sign-on is easy and manageable.
Okay.
The hardware tokens are going to be expensive.
Okay.
It's a token for each person.
Okay, so hardware tokens are, in terms of cost, probably one of the worst ideas because you have to give every Concordia person a hardware token. They have to come in person. They have to get it. You have to link the token to their account. They lose it, then they're coming back for a new one. So it's just like a deployability nightmare, right?
The manager is gonna require subscription.
Okay, so possibly, yeah, depending if it's a third party or what it is, yeah. So single sign-on, it also depends on where the sign-in is. But one thing it does require is a new server. So you're going to have a server that has to handle all this sign-on stuff, and it's going to have to handle it for all of the different services that people are using. And so that server is going to get hammered. So that it's another infrastructure cost. Yeah. What about biometrics? Could to get into Moodle, can we just switch to fingerprints?
No, we couldn't.
Okay, why not?
It should be fine because every person has a device and their device already has a biometric which is valid and
Do they?
verified by them.
Do they though?
The thing is, we couldn't because there would be no way for Moodle to take the solid biometrics. We could use like cryptographic keys, but we would need to deploy them beforehand.
Okay, so there's a couple of problems here. So the first is, do users have devices capable of reading fingerprints? Maybe, maybe not. But even if I have a MacBook that has it, does Apple give Concordia the right to read a fingerprint through its fingerprint reader? It doesn't, right?
It could probably do the verification on its side and then just give the answer.
So potentially,
So something
yeah.
like, for example, Apple Pay, you're using the Apple service to pay them, but the verification is being done by Apple.
Yeah, so that actually is exactly what secure keys is it's basically like, because this person authenticated with their biometric, I'm now going to give you a cryptographic attestation that they did do that, and then you can accept that as authentication. Yeah, the problem is I don't have fingerprint on my phone, so now I can't do Moodle on my phone. And not everyone, despite what you say, not everyone's going to have a laptop that has a fingerprint reader. Not everyone will have a laptop, period, necessarily, yeah? If you're on a desktop, you won't, so yeah. Then the other question is like, how do you get everyone's fingerprint? So now when we get our student cards or whatever, we also have to scan our fingerprints. Do we like that? Do we like Concordia having our fingerprints? Maybe, maybe not. I went to Disney World. We had to use our fingerprints to get in. It was like kind of sketchy, but.
Also, there's a side cost to restore all the biometric data.
Sure.
On a new server.
Yeah, exactly. Yeah. So you have to store it, and now it's like images, so maybe it takes a little more.
It's a lot of students.
Yeah, and a lot of students as well. Yeah. Say it louder. Yeah, the database could get leaked too, and then again, you have this sort of hash problem. But yeah, then now people's biometrics are floating around the internet instead of just their passwords. You can't change your biometric. I mean, you have 10 chances, I guess, but once you've used all 10 fingers, you're not going to be able to change it again. Anyways, okay. Let's see what I had for my list. Okay, so we talked about the expense. Do we need new servers to put up? Do we have to change the client side? So like, do we have to change how their browser works? Do we have to put an app on their phone or on their device? That kind of thing. Do they need a password manager now? Other things they consider in the paper is like, has the technology been around for a while, or is it something that like someone thought of last year? And how open is the protocol so that other people can kind of plug into it and you can have some transparency in terms of what's going on. Okay, and then the reason we're all here, security. Are these all, would you say, equally secure, or are some of them more secure than others? So just set aside, who cares about usability, even if it's worse on usability, even if it's super expensive, just set that aside. Just purely on security terms, which of these are better than others and why? Okay, passwords are weak. Why are passwords weak?
Because it could be stolen by at many points before it accesses the server, and even if it accesses the server, they could get leaked if the server is not handling them properly, or they could get broken at some point.
Okay, so there's the whole governance of the password itself, from the user all the way to the server and where the server's storing it. So that is weak, but most of these have a similar property. Usually you have to store something to recognize the user. So I don't know that you get away. We could go through them, but I'm not sure you get away. The reason I would think passwords are weak is because they're human chosen. They're easy to guess, usually, yeah, or low entropy, yeah. Okay.
Factor authentication depends on the form that you're going to use. So some forms are authenticator app on the mobile phone, it's better than using something that's related to the SIM card, which can be stolen or maybe made a copy of.
Sure. Yeah. So we'll talk about SIM swapping attacks much later. But definitely, like, the reason we have authenticator apps now is because if your text messages get routed to someone else's number, then you've broken two-factor authentication for them.
Biometrics is strong, but it cannot usually be used alone. So it's usually a wrapper around something that is already set up, like cryptographic keys.
Okay, yeah. So biometrics, well, I have a slide about it a little later, but they tend to be not as random. You basically can live in three worlds. There's like a user chooses a secret. They're not going to do a good job of it. In the middle, you have like a human is born with a certain random pattern on their body, and that's usually a little bit better than something they would choose themselves. And then you have like a machine chose it, and it's 100% random as insofar as a machine can generate randomness, and then that's like very, very strong kind of thing. Yeah. So the ones that have machine generated randomness would be two-factor authentication, because that code that you get is random. Right? So that's why it's augmenting your password with true randomness. It's not forcing you to memorize it, right? That's why it's serving it up to you. But the adversary still needs it, and the adversary is going to have a hard time guessing it, even if they can guess your password. So that's like the whole motivation behind two-factor authentication. Cryptographic keys are random, like as random as you can get. Password managers will choose, if you let them choose the password, not just store it, they'll choose a random password for you. And so, in my opinion, if you have a password manager, you don't need two-factor authentication, really, at least from a randomness perspective. Hardware tokens will have randomness, and single sign-on will be as strong as your master password on your account, which is probably human-chosen, therefore not strong. Okay, so that's like sort of the strength of them from a guessability perspective. Are there other security considerations beside that? What if an attacker wants to keep you out of, like lock you out? So remember STRIDE, so we have like denial of service. Are they all equal, do you think, in terms of denial of service?
No. For passwords, they could easily block the account or overflow it with too much requests, so we usually block the account for a certain time.
Yep, sure. So you could, I could log in with your account 10 times with the wrong password and then lock you out for 30 days or 30 minutes or something.
After, you could spam the server and keep sending requests to the owner of the...
Okay, so
There was a story about Uber, I think, where someone kept sending two-factor authentication to someone, and the person had enough and just accepted the request at some point, and the person could enter the account on the Uber chain of service or something.
okay, that's interesting. Yeah, so you could annoy the user enough that they just try and get rid of it. But you can, anything that has a server in the middle as well, you could try to attack that server and take it down.
Can do a phishing.
Okay, phishing is another great example. So is there a difference in terms of phishing between these? Are some of these easier to phish than others? Let me put it that way.
Some cannot be.
Some are way easier. Password, for example.
Okay, so a password you can phish. You go to the wrong website, you put the password in, you get phished, right?
Password is complicated to phish because it's going to be, you have to phish at the same time as the request goes, and the person has to be fast enough and understand that and believe that the person is two-factor.
Okay. So two-factor, this is how I would phish with two-factor. The user would come to my fake website. They'd say, this is my username password. I would take their username password and submit it to the real site. The real site would say, you need to enter your two-factor authentication. Then I would go back to the user and say, okay, you have to enter your two-factor authentication. They give it to me in the middle, and then I just give it back to the website. So if I'm storing passwords passively, it won't work because I won't get their two-factor. Or I'll store it, but then by the time I try to break into their account, then it's already expired. Yeah, I could steal the session, but the session won't live long enough for me to steal it. But if I'm in the middle and I'm stealing it, if I'm getting access at the same time that they're actually authenticating, like it's a real-time active attack, then two-factor won't save it. Yeah.
It's a targeted phishing. Or
Yeah. So for targeting phishing, I'd probably be real-time in the middle, and then. But even for like just phishing everyone, Yeah, so targeting phishing we sometimes call spear phishing, and we'll talk about that as well when we talk about social engineering. But is there any of these that are resistant out of the box to phishing? So yeah, sort of.
If you install a malware in the kernel level, you can access the cryptographic.
Sure. But what about just a phishing website? So I lure you to my website. So with cryptographic keys, it depends on how it works. But if I'm just like, what's your key? Then, and the user says, okay, send the key, then it's not going to help. There is one that actually helps. You might not think about why it helps, but it does. So the one that helps is password managers. Why does that help?
Because you have to explicitly specify the website, and it won't prompt you to enter unless it
Exactly. Yeah. So a phishing website is a website that looks like my real bank thing, but it's not actually my real bank website. It's not at that URL. My password manager will be like, I've never seen this website before. You don't have a password that's saved for it. It doesn't stop me from like being like, oh no, I'm sure I have it. I open the password manager up, I look for RBC, and then I copy paste it. But at least out of the box, it's not going to just paste my password into a phishing website.
Just the thing is that sometimes you have the website that has different login, the domain name. Sometimes you get used, I use a lot of password manager, and sometimes you get used to having a website that has not the same name as the one that is saved. So you just get used, so it would just be a little annoyance, but it wouldn't stop anyone from being a protection or anything.
Okay, so that's possible too. Yeah, so you sound like someone that uses a password manager a lot. So a lot of times you'll be logging into RBC, but they'll have like a different server that does their login authentication and then passes it back to RBC. And so my website was saved, or like I'm logging into TSN or Bell or Crave. They're all owned by the same server, but like my Bell password doesn't copy over to my TSN password, even though they're all the same kind of thing. And so you, as a user, you often are going into your password manager and taking a password that you have saved for one website and using it on a different website.
subdomains?
Yeah, so subdomains, usually the password manager doesn't care about, because the assumption is that the top, if it has the same like domain, not top level domain, but the same domain, then it will, it's owned by the same people, even if they're different subdomains. But yeah. Okay, let's see how we did. All right, so we talked about guessing. Another thing we didn't talk about is impersonation. So like pretend I'm pretending to be you. How easy or hard is that? So if it's a password that you chose, maybe I could guess it if I know a lot about you, right? But if it's your fingerprint, I don't know it any more than anyone else's. We can think about malware. So if there's malware on the machine, does that impact things? If there's a keystroke logger, or someone's looking over your shoulder, like the Edward Snowden thing, if it's a password manager, someone looking over your shoulder doesn't matter, right? Because the website, your browser just puts it, or your operating system puts it directly in the website. But if I'm typing it in, then I care about whether people are watching. Phishing, we talked about. Theft, can I steal something? If I steal your RSA token, what does that mean? Doesn't necessarily mean they get into the account, but we can think about that. And then another one too is, we didn't talk at all about privacy, but why is it that, I sort of gave the answer before the question, I should have asked the question first. Why is it that Facebook is so generous that they let you, you start a game and you release it, and instead of you having to deal with usernames and passwords, Facebook's going to do that for free. Yeah, so advertising and also just data, right? So they know every time someone plays that game, Facebook knows what game they're playing, they know who they are, and every other thing that someone's used single sign-on with, they can triangulate all of that data, so they get a much richer profile of what the user is, okay? So single sign-on, it's a nice solution, but it's not always benevolent, right? Like Google's not doing it because they're, they care about security necessarily. I mean, they do care about security, but that's not like their primary motivation. For doing it, they want that data, right, that comes with single sign-on. So single sign-on, you have a trusted party, and then you also have a privacy consideration as well. Okay. So now what we'll do is we'll kind of walk through it one by one. By the way, I usually have a break in class, but today's lecture is also shorter than the full thing. And so we'll just go through the break. If anyone needs to use a washroom or something, go ahead. But we don't have like a lot of content left as well. And then I think next lecture we start doing like full lectures. But anyways, I thought I'd just mention that. Okay, so now we can think about each property one by one. So I'm not going to do all the properties, but we'll do a couple of them just so that we get a feel for it. So let's start with easy to use. You can also define it as physically effortless. So it's easy. Easy is kind of vague. What does easy mean? Well, we're talking about the physical, like doing it physically kind of thing. Okay. So what we need to do for every column is, first off, it needs to be worded positively. Do you want your system to be easy to use? Yes, right? So if you get a full dot, you're happy, right? So as opposed to, I wouldn't call the column hard to use. It would still measure the same thing, right? A system that's hard to use and a system that's easy to use, you would just flip the dots around, right? So it would convey the same information, but it will make the table harder to read because now the person reading the paper or the table has to think about, okay, is this one of the columns I want, or is it a column I don't want? Right? Like I want the full dot or I don't want the full dot. So what we do is we always make it so you always want the full dot. Okay, so the full dot is always the thing that you want. Okay, so it's easy to use. And then we can define the criteria itself. Okay, so this is an example. If I have to type something, draw something, or copy and paste something, we'll say that that's some amount of physical effort. And if I have, let's say, 1,000 websites, and I log into all of them one after another, okay, there's a world where I have to do I have to type 1,000 passwords in, or I have to draw 1,000 passwords, or copy 1,000 two-factor codes, okay? So in that case, we're going to give it no dot. We're going to say you don't get the property, okay? The flip side is I never have to type anything ever. So I can go to those 1,000 websites and I never had to type anything once, okay? So that's the best world, so we'll give it the full dot. And then sometimes in the middle, I have a middle category, would be like, I have to put one password in once. So for example, if I have a password manager, I put my master password in, I unlock it, but then when I go to the 1,000 websites, I don't have to type anything in again. Or with single sign-on, I type my one password into Facebook. Now that I'm logged into Facebook, then I can log into the other 1,000 things without having to log in again. Okay, so that gets the half dot. Now you might argue that that's as good as a whole dot, but then you might also argue that most people aren't logging into 1,000 websites, they're only logging into 3, and the difference between 0 and 1 when you're only logging into 3 things is more significant, right? So how you define half dots, again, it's kind of an art, not a science, so different people may do it slightly different, but this is something that we can pencil in and then try and play around with. For nothing to memorize, again, we'll just do like no memorization. You have to memorize one thing, but if you memorize that one thing, you can use lots of different accounts for it, or you have to memorize basically one thing for every account. For something to carry, if I don't have to carry anything, again, I call it nothing to carry as opposed to something to carry because I want to carry nothing. I want the full dot. So the full dot is the thing I want as a user. So nothing to carry, that's fine, full dot. If I have to carry something, I'm not getting the full dot. But I might distinguish here between, like, is it something new that I wouldn't normally be carrying around, like a token? Or is it something that I'm carrying around anyways, like my phone? Okay, so I might decide if I have to carry something that I'm usually carrying around, like my phone, it's still not as good as not carrying anything, so I'll give it a half dot. Yeah, but again, you may come up with different versions of what a half dot is for you. Okay, we can think about guessing attacks. So is it resilient to guessing attacks, or is it vulnerable to guessing attacks? So guessing would be the adversary tries to, just tries every combination until they get the right one. And this one's sort of a complicated sort of scenario to decide which is which, so I'm just going to spend a little time talking about guessing attacks. So first off, the terminology that's used in the paper is online versus offline guessing attacks. So an online guessing attack is when you have to go through the server itself in order to guess. So example would be, let's say I'm trying to log into your bank account. So I go to the banking website, I put in the username password, it says it's the wrong password, then I try a different password, and then I try a different password. But in every case, the bank is between me and your guessing. Okay, so they're servicing all the guesses. Okay, so first off, I can't go super fast because the bank needs to be able to keep up. Secondly, once the bank sees that I guessed wrong 3 times, then they might lock me out of the account. And so I have to stop guessing at least for a period of time. And if I'm hitting it with a lot of traffic, they might look at my IP address and just block it. Or they might have intrusion detection systems that try and block it even without anyone looking at it. And so basically, I'm not going to get a lot of guesses with an online attack. Okay. Now, I can still probably crack some passwords. There's some certain categories of human chosen passwords that I could probably do a pretty good job with, even if I can only guess 10 passwords a day or something like that. Okay, I'll give you an example in a second, which would be like a 4-digit PIN. So I'm not comfortable saying that passwords even resist online guessing attacks. I think they don't necessarily. Okay, but something like a biometric probably would. Okay, so it's probably random enough that if someone's slowed down by just guessing and guessing and guessing, they probably won't get it. And they're definitely not guessing a cryptographic key, even if they could guess a lot faster than that. Okay. An offline guessing is when you have access to the back end of the system, so you're not going through the bank, no one's slowing you down. The example that would be nice would be you grab that hashed password list, so you have the hash of it, and you're just guessing, you're hashing and matching, and you're doing that all from your own computer. You're not talking to anyone, you're not going out on the network. As fast as your computer can do it, or you have GPUs, you're parallelizing it, that's as fast as you can guess. Okay, so that's an offline system. Now we need a lot more randomness in the password because we can guess a lot faster. Okay, and so things like biometrics probably don't have enough randomness to resist an offline guessing attack, but something like a cryptographic key that's 256 bits of pure randomness is still resilient to an offline guessing attack. Okay, so if you want to think numbers, you can think of like if there's over 2 to the 64 combinations, then we'll say it's sort of online guessing. So I think like fingerprints and things like that have about 2 to the 40 combinations. And then cryptographic keys are things that have like up to about 2 to the 112 or 128 different combinations. Okay, now I want to show you one other thing to motivate that human chosen secrets are unlikely to resist even online guessing where you only get a few guessing attacks. And so this is something from a paper that studies pins. And so this paper is pretty old, but the story behind the paper is that there was a website. It was called RockU. It was like a social media website, but like a really long time ago. And it specialized in music, or it sort of appealed to like fans of music, and it had a bunch of music stuff on it. That's why it's called RockU. And they had no password policy, meaning you could pick any password you wanted. You could press the space bar once and that could be your password. Okay, no minimal characters, no special characters, capital letters, numbers, none of that type of stuff. Okay, so what a lot of people did, and it got dumped, so we can see all of the passwords that were registered. Okay, a lot of people, what they did, because there was no restriction, is they chose a 4-digit PIN. Okay, probably because it matched their banking PIN or whatever. It was something they could remember anyways. All right. And so what this paper did is it just took all the passwords of people who picked a 4-digit PIN. It ignored everything else. And it just said, how secure is 4-digit PINs? Because whatever we can learn from this data leak could apply to other systems like banking passwords and things like that. Okay. So what they did is they created this picture, which just looks kind of like noise. But this is like absolutely one of my favorite pictures in all of computer science. And you're going to love it by the time we're done, when I explain to you what it is. Okay, so first off, a 4-digit PIN, how many 4-digit PINs are there? Okay, so, sorry? You're so close. How many 1-digit, yeah. So 10 to the power of 4. Yeah, but what is that? It's a number that we all know that we could say. 10,000? Yeah, 10,000, right? So it's going to be between 0000 up to 9999. So that's 10,000 different pins. Okay, could I possibly show you 10,000 things? Could I fit it on a screen? Could this have 10,000 little squares in it? It could, okay? So that's exactly what this is. So this is a visualization of all the 10,000 possible pins. There's only 10,000 of them. They do fit on a screen. It's kind of small, but you can see them, okay? And they're organized where the first 2 digits are in the x-axis and the last 2 digits are in the y-axis, okay? And so if you want to read out a password like, say, 1234, what you would do is you would find 1, 2 along the x-axis, so you go to 12 here, and then you would go up to 34, and then you'll find the digit 1, 2, 3, 4 right there, okay? Now, 1, 2, 3, 4 is really dark, okay? So you notice the colors are different, all right? What do colors mean? Okay, most common. So the more someone chooses someone, the darker this cell is. It's on a logarithmic scale if that means anything to you. So it means that, like, if it's really dark, like lots and lots and lots of people chose it relative to almost no one, okay? So when you look at this picture, let's say that everyone chose pins at random. Say the system just assigned them pins at random. What would you expect the color of this picture to look like? Okay, so it would be like a mid-blue, but would there be like patterns or dark squares or anything? Okay, it's going to be uniform, right? It's basically just going to look like a wash out. It might be a little staticky or whatever, but it's just going to look like a wash. Does this look like that? Absolutely not, right? There's patterns, there's lines, there's streaks. What does that mean? That means that there's passwords that are more common that people like to choose than other types of passwords, okay? So what are some 4-digit pins that people might want to choose? Okay, so a birthday is a good example. So what's your birthday and what's your 4-digit pin? You can make it up if you don't want to reveal your real birthday. 0406, all right. And is that March 6th or is that June 4th? Okay, so let's say it's March 6th, so date, month. Or sorry, we'll say it's month, month, date, day. So that's exactly the kind of thing that would get popularized. Okay, so where would we find these passwords in this table? Okay, so at the beginning, okay, so where does month, month, what's the range for month, month? Okay, 1 to 12, 1 to 12, right? And for days? Yeah, it's kind of variable. So if I look here, I see there is a square like here that goes from 1 to 12, it's kind of darker. And then if I read off, you can see there's kind of, it looks like a castle or something, like the moats of a castle. And if I read it off, moat's the wrong word, I forget what they call it. But for 1, it goes up to 31. Then it goes up to 28, 29. Then it goes back to 31. Then it goes to 30. Then it goes to 31. So what is that? So those are the days in the month kind of thing, right? Okay. And then you'll notice here I have the exact same pattern, kind of flipped. And that's because not everyone does month, month, day, day. Some people do day, day, month, month. Okay? And so what's kind of cool about this is, say you're an alien and you don't know anything about human society, and all you know is the 4-digit pins that people tend to choose, then you would know at least the one kind of calendar that people tend to use. You could read it out of the passwords that they chose. Okay, what are some other 4-digit things that people might like to choose? Okay, so I heard years and some other stuff. Let's go, I think years is next in the slide anyway. Okay, so what are some years that people would like to choose? I mean, any 4 digits could be a year technically. Okay, so they're probably going to pick a year like that they were born or at least were alive or that type of stuff. So if we try and find the 19s, you'll see the 19 is here. And so you'll see this line here. And it gets darker and darker the higher you go. So this is like kind of 1960, 1970. It gets darker, 1980, 1990, 95. Then it flips down to the 2000s, and then it's pretty dark. And it goes up to about 2010, which is 2015, which is kind of when the site was broken at that particular time. Okay, other lines that you can see or patterns or things? Okay, so there's a diagonal line across the middle. What is the diagonal line? Okay, so it's like repeated digits. So for example, 444, it would be this one. 777 is this one. 6969, don't know why, is very popular. There's things like 1234, so that's an example. 2468 is another example. 976. And so like anything you can think of, you could probably find on this picture, and you could find like a dot for it. Then there's other references to things like, so I can't explain this properly, but believe it or not, there was a time when phones didn't have touch screens. And so if you want to send a text message to someone, like if you have A, you type like the number 1. If you want B, you type it twice. So like ABC, you could type with the number 1. So anyways, if you type out 5683, it spells out love in SMS. Because it's a music website, sometimes bands have albums that have like 4 digits. And so these tend to be popular. So Usher has an album, Van Halen has an album. And anyways, these are just some of the things that are here. If you wanted to, you could spend some time like looking at it and being like, oh, this dot is like really dark, like figure out what the number is and then Google it or ask ChatGPT like why is this a significant number? And there's usually some reason behind it. Yeah, so anyways, you can spend a lot of time looking at this. Okay, we'll go back to the security properties. So shoulder surfing, it's either resilient or not. Physical theft, either resilient or not. Cost, so if it doesn't cost anything, that's good. If I have 10,000 users and I have to pay 10,000 times, that's going to be expensive. If I have to pay once, like say I set up a new server, but it doesn't matter if I have 10 users or 10,000 users, then that's a cost. It's worse than not paying at all, but at the same time, it's not like buying everybody an RSA token or buying everyone a fingerprint reader that they can plug into their computer. Okay, so then the evaluation framework would look like this. Okay, so we can just sort of walk through it column by column. So usability 1 is easy to use. So the ones that are easy to use don't require you to ever type anything in ever. So biometrics would get that, and cryptographic keys, they just happen. Now you might argue, well, with biometrics, you have to put your finger down. So if you want to consider that a half dot, that's fine too. Different people, like I say, will define dots differently. Managers and single sign-on, I gave half a dot because you usually have to sign in once to unlock it or to log into Facebook. But then once you're logged in once, then it's okay. And then everything else is sort of one password or password plus authentication token per account. Okay. And because I did a good job of really crisply defining what it means to get a full dot, a half dot, and a half dot, it's more or less obvious why a system gets a dot or not a dot kind of thing, right? So if you spend a lot of time like writing really crisp definitions, then it makes it a lot more readable. It's less controversial, like, oh, why are you punishing graphical passwords? Like they look terrible on this table because they don't get a lot of dots or whatever, but everything's very objective, it's neutral. Anyways, okay, let's keep going. Nothing to memorize. So this actually mirrors this column, which is the same, like if you have a fingerprint or a key, you don't have to memorize it. For these ones, you have to memorize one thing. And then for the other ones, you don't have to memorize it. Now, another thing that will come up when you do these evaluation frameworks is if you ever get 2 columns and they look identical, so here these 2 columns look identical, you have to ask yourself, are they actually different properties? Or am I just measuring the same thing twice using different words, okay? So you don't ever want to measure things differently, right? Or you don't want to have multiple columns. The other type of pattern you might see is a flip. So you might have one column and another column's exactly the flip. Every time it gets a half dot, it gets a half dot. If it gets a full, the other one gets an empty, and vice versa, okay? Now the reason why these 2 are the same is because if you have 0 passwords, you get the dot. If you have 1 password, you don't. And if you have 10,000 passwords, you don't get the dot, okay? But are they actually the same property? They're not. Okay. Then you could ask yourself, is there something that would be like easy to use, but would require more memorization, or vice versa, that requires a lot of memorization, but is not easy to use? And you can try and come up with examples of things that would split it, even if they're not in your table. And if you can do that, then that also indicates to you that there are different actual properties and they belong together in a table. Nothing to carry is pretty straightforward. So tokens, you have to carry something so they don't get the dot. two-factor authentication, you have to carry your phone, which you're probably carrying anyway, so we give it a half dot. Everything else is fine. It gets the full dot. Guessing, it basically just comes down to how random things are. So if it's human chosen, I don't give it the dot on either. If it's some sort of natural phenomena like your fingerprint, I give it the dot where it's resilient to online guessing but not offline guessing. And then if it's some sort of machine-generated randomness, then I'll consider it resilient to even to offline guessing. So that's sort of the pattern that's there. So biometrics gets a half dot, and then the machine-generated ones would be like the RSA tokens always giving you a random number, two-factor authentication's always a random number, and cryptographic keys are random numbers as well. Why is, sorry, oh, just because I can guess your master password. So the master password, yeah, and same with password managers. So password managers also generate random passwords, and so the per site passwords are resilient to offline guessing, but the master is not. Then you have to decide what to do with that. So how do you want to reflect that in your table? So you might invent other columns that are slightly different to try and get that point across.
For the SSO, you wouldn't be, like, you usually don't get the hash or anything from the master password, so you would have to ask yourself every time.
So the idea is that I could guess, it's just simple, like I guess your Facebook password. So I think you're using your dog's name and your birthday or something like that. If I'm right, I guess it, now I get compromised to all your websites.
Yeah, what I mean is that it wouldn't be resilient to offline guessing.
Exactly, so it doesn't get the dot. So it doesn't get either dot. I think what's tricking you up is the, like the phrasing of it, right? So full dot means it does resist, it's secure. And no dot means it's not secure in this case.
Okay.
Does it make sense?
Because for me, you could only guess it through online guessing. For offline.
Oh, so if you can break online guessing, you can also break offline. So like, also notice that there's no, you can't not get the dot, whoops. There's a combination missing, which is that you don't get the dot here and you get the dot here. And that's because it's strictly harder to do an offline guessing attack. So if you,
It could be easier to try on the site instead of obtaining the database.
yeah, I see. So this is, so this would require further phrasing. But the assumption I would make is I'm assuming you already have the database. So I'm not accounting for that factor itself. Yeah. So, yeah, okay. Shoulder surfing. So passwords you type in. A token, you're typing it in, and two-factor, you're typing it in. Graphical, you're swiping it in or whatever, but you're still, someone that's looking over your shoulder can get it. Biometrics, there's nothing to see. Keys, there's nothing to see. Password managers and single sign-on. You have a small window of time when they're putting that master password in. If you could shoulder surf them then you could get it. But if you don't get it then, and then they're walking around signed in, then you're not going to get anything else from it. So that could be a half dot. Physical theft, so kind of morbid to think about, but I can steal your finger, right? And I can sign in for you. You see it on lots of spy movies and things like that. It actually doesn't have to be that morbid. I could actually lift it off like a glass or something like that, or I could steal your physical finger. And keys also are something that are sitting on your computer. If I get access to your computer, I just copy the file, or I get malware on your machine or something like that. The first thing malware does now is it looks for Bitcoin keys on your computer, and so generally you would wrap the key in some other thing, but anyways, if it's just a naked key that's sitting there in plain text, it could be stolen. And then in terms of cost, biometrics cost something if you assume that people don't have readers already, and tokens cost something because you have to give them out. And single sign-on, I gave it a half cost because you have to put a server up in order to handle that traffic, or get Facebook or someone to do it for you. So there's a one-time cost, and then everything else is just, it costs the same as passwords, not any more or less. Okay, so you look at this table and you ask yourself which one's best. So which is the best password alternative? Okay, so you might be tempted to say keys and biometrics. Why do you like those? It's sort of obvious, but just,
They are the one that has the most
okay, they had the most dots.
Or we choose the best.
Yeah, okay. But first off, yeah,
Doesn't kind of depend on like, what you're looking for?
yeah, 100%. Thank you. So does the most dots mean that it's the best? Not necessarily, right? What if S4 is the most important property for me? It's the only thing I care about. I don't care about anything else. I only care about S4. Then is cryptographic keys going to be the best? It won't be for me, okay? So the point of an evaluation framework is actually not to sell you and say it's the best. And we don't put like numbers here like 3, 5, and count up like the number of dots and say this one got the most kind of thing. It's really about, again, presenting the trade-off, right? So different people will care about different properties more, or like cost might be like one that you really care about or you don't care about at all, depending. And so like military use RSA tokens. Do they care about the cost? They don't care. It's top secret. They want the highest security. They don't care if it's not that deployable or it's not that usable. As long as the security properties are looking good, that's like what they care about the most, right? And they don't use it for everything, right? You're not using it for your social media or whatever. You're just using it for classified files or whatever, right? And then a university is going to be somewhere in between. And then there might be different systems too, right? So like, for the long time, Moodle didn't have two-factor authentication because it's just Moodle. Who cares, right? It's not your student account where your banking information and your social insurance number and stuff like that is sitting. There we'll use two-factor, but for Moodle we won't. Now it's like, I think they rolled it out everywhere. But yeah, so the point is that you try and evaluate trade-offs. Now, as I mentioned, I drew this out of a paper, the idea for this. And so I just want to show you a bit of the paper itself. So it's a little small to see, but the first thing I want to impress on you is that they evaluate a lot of systems beyond what we did in class. They also kind of break them down. So instead of like for example, we just said biometrics broadly, but they compare fingerprints to iris to voice. And then, instead of RSA being the only hardware token, there's YubiKey and IronKey. And this paper is a little old now. I think it's about 10 years old or even older. And so some of the newer stuff won't be on here exactly. So they have different OpenID. Federated is what they call single sign-on. So, Microsoft, Facebook, browser ID was something that Mozilla did for a while. And yeah, anyways, there's a bunch of different kinds of systems. You can see they have a bunch of different properties. So I tried to choose a subset of the properties that they use, but they have a lot more than what we talked about. So I can actually just read them off. So for usability, memory-wise, effortless. We had scalable for users is sort of a different property. Nothing to carry, physically effortless, easy to learn, efficient to use, infrequent errors, easy recovery from loss. Deployability would be accessible. So it's something we didn't talk about, but users have disabilities, and so that may prevent them from using particular systems depending on what the disability is. So that's another consideration. Cost, we talked about server compatible, browser compatible, meaning you don't really need to change the server browser. Mature, non-proprietary. And then security, so physical observation would be like shoulder surfing. Targeted impersonation would be like, can I guess your password if I know a lot about you? Or can I authenticate as you if I know a lot about you? Throttled and unthrottled guessing is what we called online and offline guessing. Internal observation is malware. So if there's some observation within the machine, internal to the machine, does it get leaked? Leaks from other verifiers would be like third parties, that kind of thing. Phishing, theft, trusted parties, so the privacy consideration, requiring explicit consent. I forget exactly what that meant. And then unlinkability is another thing where it's like, can you figure out that it's the same user on multiple websites? So some of them are purposely unlinkable so that you can have different accounts. And if, say, like Facebook goes and buys a company and you're a user of that, like say it's a game and you use that game before, they don't necessarily strictly know that it's you, even though you have a Facebook account as well. Okay, so in an assignment kind of thing, you would probably do something a lot more complicated or like a little more detailed than what we did in class, but it wouldn't necessarily have to be as detailed as this. This is a paper at like the very top conference in security. If you want to do a class project and you're like, I like this evaluation framework, you could do that as well. And in that case, you'd want something that's like maybe not at the level, it wouldn't probably reach the level of this, but you want something that looks a lot more like that than it looks like this kind of thing, right? So a lot more detail about a lot of different systems and different properties that you could come up with. Okay, questions about evaluation frameworks? Okay, oh yeah, one thing I'll read is a quote from the paper. So if you look at this again, like which system is best, you could ask that question again for this. Again, there's not a clear answer. Even if you count the dots up, it's probably not going to be that informative. And what they say at the end of the paper is, not only does no known scheme come close to providing all the desired benefits, meaning no scheme gets dots all the way along, none of them even retain a full set of benefits that legacy passwords already provide. So everywhere there's a red cell, it means that it's missing a property that just normal passwords have. And every time there's a green cell, it means they get a property that normal passwords don't. So you can see there's a lot of red cells. There's also a lot of green cells. So everything like makes something better, but it makes something else worse. There's trade-offs. Yeah. So in particular, there's a wide range from schemes offering minor security benefits to those offering significant security benefits, but in return being more costly to deploy or more difficult to use. So there's a trade-off essentially between security, usability, and deployability. And an evaluation framework is a good way to get that across because a lot of times you're just trying to evaluate things. You're trying to be neutral. It's not your job to pick what we use. It's your job just to lay out what the alternatives are. Someone else is going to do the picking for it. And so this is a good approach for any scenario where you find yourself like that. Okay. And then assignments, I'm not going to talk about because I haven't figured out the assignments quite yet. So when I release the assignments, I'll come back and I'll talk about it then. Okay, any final questions? Okay, sounds good. So I'll see you all next week.